In this screencast, we are going to continue our discussion of Chapter 8. We've talked a lot about energy, and now we're going to talk about enzymes. Okay, so a catalyst is any agent that speeds up a reaction without being consumed or changed by the reaction itself. Okay, and an enzyme is an organic catalyst. So enzymes are the catalysts that exist in living things. So enzymes are catalytic proteins. Okay. So if we look on the next slide, we're going to look at hydrolysis of sucrose by the enzyme sucrase as an example of an enzyme catalyzed reaction. So we have sucrose here, which is a disaccharide. Water is added to hydrolyze that bond, and to make it easier or faster, the enzyme sucrase, I don't know what I'm doing there. The enzyme sucrase is going to catalyze this reaction and make it go faster. And so sucrase helps to divide the sucrose into two parts, glucose and fructose. And we know it's an enzyme because ASE. All right, so how do enzymes make reactions go better, faster, more efficient? And they do it by affecting the activation energy. And what the activation energy is an initial energy that is needed to start a chemical reaction. Okay, so it's called the free energy of activation, or the activation energy, EA. So every single chemical reaction involves breaking bonds or forming bonds between molecules. And this is kind of, you need a little push to get things going. And that's what the activation energy is. So activation energy, the energy for the activation, is usually supplied in thermal energy that the reactant molecules absorb from their surroundings. So some of that heat, okay, where all of our entropy is stored, can be used to put back into reactions in order to supply activation energy. Okay, so here we have the energy of our reactants and the energy of our products. If we look at this one, this is an exothermic reaction because the energy of the products is less than that of the energy of the reactants. So our delta G is going to be less than 0. It'll be negative delta G. Okay, so this is exothermic. And exergonic. Exergonic. Okay, reaction. But you'll see, even though there's going to be an overall release of energy, there still is this amount of energy that needs to be put in. Okay, and that's the activation energy. Okay, it just gets the reaction going. It gives it a little push, and it takes basically the reactants and stresses them, adds some stress so that they become more volatile, they become more reactive, and then they can more easily be converted into products. So enzymes catalyze reactions or help reactions go smoother, faster, better by lowering the energy of activation. Okay. They don't affect the change in free energy released. They basically hasten reactions that would occur eventually. Okay, so here if you look at kind of that same reaction, so again, this is exergonic. Okay, the energy of the reactants is more than that of the energy of the products. Okay, so the delta G is unaffected. It's still going to be a negative delta G. And with the enzyme, without the enzyme, we have our regular activation energy. And with the enzyme, this red line, you'll see the activation energy is much less, okay, lower with the presence of the enzyme. So it's easier to get the reaction started, and reactions will therefore go faster. So the reactant that the enzyme works with is called the enzyme's substrate, okay? And the enzyme will bind to the substrate, to the reactant, and form an enzyme substrate complex. And this is an extremely specific interaction. There are hundreds of thousands of reactants that are going to participate in hundreds of thousands of chemical reactions in your body. And every single one has its own personal specific enzyme. So there are, of course, also hundreds of thousands of enzymes that catalyze those reactions. Okay. The substrate binds to the enzyme at a place called the active site. So active site is the region on the enzyme where the substrate binds. Okay. And again, it's a very specific interaction, perfectly shaped. And what we get in the substrate enzyme interaction is something we call an induced fit. Okay, so a lot of you learned this in grade school or middle school as a lock and key interaction, but that's really not actually what happens. Lock and key is a little bit too stiff, too unyielding, too exact. And it's a little more pliable than that. So when the substrate binds, it brings chemical groups of the active site together in a better way so that the fit gets even better and the reaction is further enhanced. So if we look here, so here is our active site. That's where the substrate is going to bind to the enzyme. And once the substrate does bind, okay, and you see the enzyme sort of almost like hugs around the substrate, and it doesn't just kind of go into the active site and sit there. The binding of the substrate helps change slightly the shape of the enzyme so that it fits and binds even better, and you get a better interaction and a better reaction. Okay, so how does an enzyme lower the activation energy? So how does this work? So the active site can lower the activation energy by doing a couple of things. It can just basically put the substrates in the right place at the right time, or in the same place at the right time. Just get them next to each other. The active site can strain the bonds in the substrate and put enough stress on them, make them unstable enough so that the reaction will occur. Provide a favorable microenvironment. Say you have some hydrophobic molecules that need to react in the cytosol. Okay, they don't like it in the cytosol, so an enzyme can provide a little microenvironment of hydrophobic. And on occasion, the active site can covalently bond to the substrate temporarily in order to facilitate the reaction, and then it'll let go. All right, so here's kind of an example of how an enzyme can catalyze a reaction. So here's step one. You have the substrates enter the active site, and you see basically this enzyme just kind of gets these two substrates in the right place at the right time. They're held in the active site by some weak interactions. And then by placing them in the active site, this lowers the energy of activation to speed up the reaction. The substrates are converted into products, and once they are released, okay? And then again, since the enzyme is not altered in the reaction, it can be recycled, okay? Active site is now back in business, open and available for substrates, and we just keep going around and around and around.